So this video we are going to discuss about the fiber, proteins and food reduce analysis. First of all, we will see analysis of fiber. So if we take fiber, actually it is not a nutrient. It's not a nutrient, right? It's not a nutrient. But it will play a very important role in human nutrition. Why? So when you consume food which contain high amount of fiber, right? It can filter, it can control absorption of certain material to the body. For example, if the food contains high amount of carbohydrate like nutrients, if you consume that food along with the fiber, right? Now the rate of the absorption of that carbohydrate decreases. Not only that, if your food contains certain toxic material, right? If you consume that along with the fiber containing food, fiber-rich food, the rate of the absorption of that toxic material to the body is reduced. That is ruled by the certain research studies, right? But there is a problem associated with the fiber if your diet contains very high quantity of fiber, right? It will retard the absorption of certain minerals. Therefore, you will face certain deficiency conditions, right? So that means middle path is the best path, right? Although fiber is good, don't consume large quantities of fiber, because if you consume large quantities of fiber containing food, right, it will retard the absorption of the minerals and other nutrients. You will face a malnutrition condition. Therefore, consume with the average amount of fiber containing food with your normal diet, right? You can maintain the better health. You can maintain the better health. So, by keeping these things in your memory, right, then we will see how do we analyze the fiber available in the food. Remember, this is crude fiber. In addition to that, there are acid detergent fiber, dietary fibers, everything, right? Before that, we are going to analyze crude fiber, right? Crude fiber means first we have to weigh the sample weight. We take W1, right? Like other analysis, sample should be representative sample, right? Then we have to mix this sample with corn sulfate. Sample of sulfuric within the round bottom class. You can use round bottom class to analyze fiber. Now, round bottom class contains sample plus, right, sulfuric acid. Right. Then we are going to reflux. The term is reflux. Reflux this sample with the sulfuric acid. So, what is the difference between refluxation and distillation? Why do we reflux the system? Why do we reflux the sample with sulfur? So, we need to keep our volume of the sample constant during the digestion. So, if you distill, what will happen? Certain amount of solvent go out. Then volume of the mixture can be changed. We need to digest the sample with sulfuric at a constant volume condition. To maintain the constant volume, we have to reflux. We have to use the reflux condenser. That condenser is not a small one, little bit long condenser we can use for the reflux activity. You have to fix the condenser to this round bottom glass. From here, long condenser, reflux condenser you can use. Right. Water inlet, water out. Right. Then you have to boil the mixture using heating metal. Right. For 30 minutes. You have to boil the mixture using heating metal for 30 minutes. So when you boil the mixture, what will happen? If there are any content which can dissolve in sulfuric acid under acidic environment, right? Dissolve and remove it from the sample. Within 30 minutes, if there are any component which can easily dissolve in sulfuric at this condition, right? Remove from the sample. Then at the end of the digestion, end of the 30th minute, you have to take this one and filter using crucible. Using crucible, we have to filter. We can use glass like this for the filtration. And fix opening of the glass to the vacuum pump. Right, vacuum pump. You have to remove anyhow. You have to remove the. You have to remove the sulfuric acid, right, through filtration. This crucible is very important because this can bear very high temperatures. Because at the end of the process, we are going to transfer the crucible into the oven. Right? Transfer the crucible into the oven. Therefore, it should have an ability to bear high temperatures. Therefore, you cannot use each and every type of crucible for this one. There are specific type of crucible for this experiment. Right? Right. Then, after removal of all the sulfuric from the sample, so how do you confirm it? You can use indicator. You can use indicator and wash the sample 2 or 3 times by using normal purified distilled water. Right? Then you have to transfer the sample with the aid of sodium hydroxide. That is again from sodium hydroxide. Now this time we are going to mix the sample with the sodium hydroxide, not the sulfur. Right? Now we are going to reflux the sample with sodium hydroxide for 30 minutes. Reflux the sample with sodium hydroxide on sodium hydroxide for 30 minutes. Right? So at the end of the refluxive process, again you have to remove the sodium hydroxide. You have to filter off the sodium hydroxide part. Right? Now the sample does not contain anything which can dissolve in sulfuric or sodium hydroxide. Right? If there is a component available in sulfur which can dissolve in sulfuric or sodium hydroxide, all these things dissolve in sulfuric and sodium hydroxide removed from the sample. Right? But the sample containing certain other things, not only fibers, sample containing certain minerals also. So at the end of the whole refluxation process with sodium hydroxide and sulfuric, right? Now we have rough sample, right? That sample contains fiber plus minerals. Fiber plus minerals. So we have to take the weight of this intermediate sample after the reflux. That is W2. But after refluxing W2. Right. Then we have to transfer this whole setup, that is whole setup in funnel with the fiber sample, the digester sample to the muffle furnace. Now the aim is removal of the fiber part from the sample. We have to practice dry ashing condition. You have to directly transfer the funnel with the digester sample into the muffle furnace. So after the ashing, right? After ashing, weight can be W3. This after ashing. After ashing operation, W. Now, what is the amount of fiber? W3 mean only the mineral. W1, 2 mean fiber plus mineral. Therefore, fiber content available in the sample. Fiber content available in the sample equals to W2 minus W3. Is the fiber content. But if you divide it by sample weight W1 and multiply by 100 to calculate the percentage of fiber available in the sample. Right? Experiment is very easy experiment. Experiment is very easy, but you have to be very careful in taking measurement weight of the samples. And this is not easy one. Filter the mixture using vacuum pump. It takes time. Sometimes it takes time, right? Anyway, this is the way to identify or calculate the crude fiber content of your sample. Crude fiber content of your sample, right? Right. Now we have already given the topics for the one topic for the one assignment based on the SDLC. Now I am going to give the second topic for the course unit based on the fiber. Right? The topic like this: compare and contrast. Write down the topic of the second assignment. Compare and contrast the methods available for fiber analysis. Right? Compare and contrast the methods available for fiber analysis. That is the second topic, assignment topics. Compare and contrast the method available for fiber analysis. The compare and contrast means you have to select at least 3 methods. Don't go for the number of, there are number of methods, but at least 3 methods you have to select available for the fiber analysis, right? Then compare and contrast means you have to think about the similarities of each and every techniques and differences. Similarities and differences you have to discuss, right? Compare and contrast means that is the meaning, right? First you have to select at least minimum number of methods, 3 methods. 3 methods you have to discuss, but when you discuss available methods, you have to compare the method. That means similarities you can compare, and differences within the methods or among the methods you can discuss, right? Right. That is the second assignment topic for this course unit, right? This course unit for the both assignment gain 40 marks. HPLC 20%, this fiber assignment 20%, both assignment gain 20 marks, 40 marks for the paper, right? Final evaluation, 60 from the written paper, 40 from the assignments, right? Right. Now we will move to the another important nutrients, that is crude protein. Crude protein. Crude protein. So there are a number of methods available to determine the crude protein. Number of methods available for the determination of crude protein. If we take names of these methods, sometimes Lin hybrid test. Lin hybrid test. Sometimes 4-mole titrate. Sometimes dye-binding method. Dye-binding method. Sometimes gel-dal method. Right? These are the few types of commonly used experiments to determine the crude protein. Right? Commonly used techniques to determine the crude protein. Out of these methods, anhydride, 4-mole and dye-binding, the best method to determine the correct protein content about the sample. Right? Out of these methods, except gel-dal, other 3 methods are more suitable compared with the gel-dal to detect the protein, determine the protein content available in your sample. Why? In case of gel-dal method, we are not going to determine protein content available in your sample directly. First, we have to determine nitrogen available in your sample, not the protein. Then, by using certain magic numbers or factors, we can convert that nitrogen amount into protein by calculation. By calculation, right? Then 100% depend on the factor, not only the experimental value, right? So the nitrogen content of the protein can easily determine by the gel-dal method, but other 3 methods directly associate with the amino acid, anhydride, 4-mole and dye-binding. Right? Directly you can determine the protein content of your sample. Right? But unfortunately, in most of the cases in the world, they use gel-dal method to determine the protein content. In addition to these three, they use gel-dal method. That means they evaluate the nitrogen content. When you try to evaluate the nitrogen content of your sample, in addition to the protein nitrogen, non-protein nitrogen can also interact with the reagents. Then it will contribute to the nitrogen. Right? But we need to analyze only the protein nitrogen, amino acid nitrogen. But you cannot analyze direct protein nitrogen or amino acid nitrogen using gel-dal method. Although the condition like this, we have to discuss all 4 methods. Right? First with gel-dal method for the protein determination, because this is commonly used method in the laboratory. In your practicals, you are going to use gel-dal method. Because not only your practicals, right? In certain experiments, specific quality test experiment. That's why few years ago, certain milk manufacturers, milk powder manufacturers add certain nitrogen sources, ECD-like compound to the milk powder to increase the nitrogen content of the milk powder. Then they prove that, right? Prove that that milk powder contains high amount of protein because they use Gel-Dal method to detect the protein. Gel-Dal method evaluates the nitrogen available in the sample. Once you introduce nitrogen through another source, right? At the end of the process, end of the analysis, the result says this contains more protein, right? So this kind of thing can be happen, right? Then if we take Gel-Dal method, Gel-Dal, the analysis consists of three main steps. Analysis consists of three main steps. First one, digestion. Digestion. Second one, distillation. Third one, titration. In case of Gel-Dal method, all method we can divide into three levels. First level, digestion. Second level, distillation. Third level, titration. So we will discuss one by one what will happen in the Gel-Dal analysis. First, if we take digestion of the sample. So how do we digest and what happened to the sample during digestion? We will see. For the digestion step, we are going to interact the sample with conc sulfuric acid, concentrated sulfuric acid. The target is conversion of all the nitrogen available in the sample into the ammonium sulfate. Right? Remember, digestion step is the very important and first step of the Gel-Dal analysis. Right? We are going to interact conc sulfuric with our sample. The objective is conversion of all the nitrogen available in the sample into the ammonium sulfate. Right? So this is very important reaction. That means if the nitrogen available in the sample will convert into ammonium sulfate. Ammonium sulfate. Nitrogen available in the sample convert to ammonium sulfate. So ammonium sulfate is a colorless. Ammonium sulfate is a colorless, right? So if you start with the colored sample, you will end up with the colorless mixture because of the ammonium sulfate. Because if you end up with the colored mixture, there will be an incomplete digestion, right? There will be an incomplete digestion, right? But there are certain exceptions. There are certain exceptions. Don't worry about that. So when you learn this thing in your laboratory classes, you cannot obtain colorless digestion mixture, digested mixture. Why? For this digestion, we have to supply very high amount of temperature for long time. Very high amount of temperature for long time. Right? That means we have to wait for long period of time for the digestion. We have to wait for long period of time for the digestion. We can't do it. Therefore, to do it within very short period of time, we have to add catalyst tablets. We have to add catalyst to convert nitrogen into ammonium sulfate within very short period of time under comparatively low temperature. Comparatively low temperature. That is not again low, very low temperature. It is around 400, 350 like this, but comparatively low. Without catalyst, if you try to convert all these nitrogen into ammonium sulfate, right, you have to go up to 900,000 like Celsius. That is not easy. That you can't do it. Therefore, we can add catalyst, right, to do this conversion. So when we think about the catalyst, there are three types of catalyst. Right? First catalyst, mercury-based catalyst. Mercury-based. Active one is a mercury. Second catalyst, selenium-based catalyst. Third catalyst, copper sulfate-based catalyst. Copper-based catalyst. Right? There are three types of catalysts available for the digestion. So if we think the efficiency of the catalyst, compare the efficiency of catalyst one by one, the highest efficiency you can obtain from the mercury. The next, selenium. So next one is a copper. Copper is the last one. Although mercury shows the highest efficiency, it can create toxic fumes, right? Very toxic fumes because of the mercury. Although mercury can help the digestion within comparatively low temperature condition and within short period of time, right? But the thing is, it can evolve, it can create high toxic fumes. In addition to that, when you use mercury as a catalyst, right? In addition to that, when you use mercury as a catalyst, certain nitrogen available in the sample and trapped within this kind of cyclic molecules. It can form cyclic compound like this. Right? If you use mercury as a catalyst, certain amount of nitrogen can form cyclic compounds. Cyclic compounds. So you cannot analyze this nitrogen using normal distillation technique because certain amount of nitrogen, generally we expect all the nitrogen available in the sample convert into ammonium sulfate. But when you use mercury as a catalyst, right? So all the nitrogen cannot convert into the ammonium sulfate. Part of the nitrogen form this kind of cyclic compounds. Cyclic compound. To release this nitrogen from this cycle, you have to break this bond. Right? To release this nitrogen for the final evaluation, you have to break this bond. Therefore, when you use mercury as a catalyst, so final distillation system, we have to add sodium thiosulfate. Right? If you use mercury as a catalyst, for the final evaluation, you have to add sodium thiosulfate. So roll up the sodium thiosulfate, break this linkage and release this nitrogen to the system. If you don't use mercury-based catalyst, no need to add sodium thiosulfate under distillation level, distillation condition. Right? That is the mercury condition. Then if you take selenium, right? Comparatively mercury, rate of the reaction is low. The highest one is mercury. Comparatively mercury, selenium, rate of the activity or efficiency of the activity low. But compared to the copper-based one, that is high. Compared to copper-based one, that is high. But in addition to that, like mercury, certain amount of nitrogen available in sample convert into nitric acid. Oxidizing nitric acid. That will be a problem. Right? If you use selenium as a catalyst, certain amount of nitrogen convert into nitric acid, oxidized into nitric acid in addition to the ammonium sulfate. Therefore, you cannot evaluate all nitrogen in your sample. All nitrogen in your sample. Right? Then if you take copper-based one, rate of the reaction is very low. Very low. Time schedule, you have to wait for 1 hour sometimes. Special machines, we have delta digestion units. 1 hour, temperature around 420, 430 like temperature, degree Celsius. You have to supply if you use copper-based catalyst. Right? But you don't face this kind of problems. you don't face this kind of problems. But using copper-based catalyst, you cannot digest all sample at a time. Therefore, in Geldal analysis, generally we assume recovery of the sample around 96%, not 100%. 100% conversion we cannot expect because of these problems. 96% of the sample convert into ammonium sulfate. In other important thing, when you use copper catalyst, right, you cannot end up with colorless solution because of the copper sulfate. Right, potassium and copper available in that. Potassium, role of the potassium salt is elevate the temperature. It will support the elevated temperature. Copper can act as the catalyst. Because of the copper, now you can end up with the blue color solution, not the colorless. But with these two catalysts, you will end up with the colorless part. Right? Then after, this is the digestion state. After digestion, then you can distill the sample. That means now your sample contain, after digestion, you collect ammonium sulfate. Now available in the Geldal tube, right? For this digestion, we can use Geldal tube like this shape, like this. Large tube, right? Now, your Geldal tube contains after digestion, it contains ammonium sulfate. Now, we have to transfer the ammonium sulfate contained in Geldal tube into the distillation unit. For the distillation, we are going to use sodium hydroxide. 8M sodium hydroxide. Or 32% sodium hydroxide. Here we are going to use sodium hydroxide because when you interact sodium hydroxide with the ammonium sulfate, ammonia can be evolved. You can release ammonia from the mixture if you interact ammonium sulfate with the sodium hydroxide. Right? So you have to do this experiment under steam conditions. Steam means you have to supply energy through the steam. We have a special machine for the distillation unit. When you do the practicals, right? When you see the practical videos, now you can observe it clearly, right? You have to supply the sodium hydroxide source and the steam to the system. Then you can observe the evolving of the ammonia from the system. Then this ammonia, we have to trap the ammonia in 4% boric acid. 4% boric acid. The role of the boric acid is trapping activity, not the interaction between ammonia and boric acid. Just trap the ammonia released from this sample. During the distillation, right? Sodium hydroxide interact with the ammonium sulfate and release the ammonia. That released ammonia trapped by the 4% boric acid. 4% boric acid. Just after trapping, right? No time to prepare the other reagent. You have to already prepare before you distill, right? During the digestion step, you have to prepare certain reagents. One is this one, 4% boric. Other one is indicator for the titration. This indicator is not a single component indicator. This is a mixed indicator. So generally we heard about methyl orange, methyl red, methylene blue, phenolphthalein, right? that kind of indicator. Here we are going to use ethanolic form of two indicators, methylene 2 and beta-enolate, 1:2 ratio. 1:2 ratio. You have to mix together to form two component single indicator. These two mix together to form an indicator. That is gel-dahl indicator. You have to freshly prepared one. You have to use freshly prepared one. That means you have to prepare it just before the analysis. Right? 4% boric during the duration of the sample you can prepare. Not only that, you have to prepare 0.02 m HCl. 0.02 m HCl. Right? Using volumetric flask and stock solution available in the laboratory, you can prepare 0.02 m HCl. Now you can start standardize your HCl solution before the analysis, because this is not a simple one. From this analysis, you are going to say this food item contains this much of protein. Not a simple analysis, right? Very big statement you are going to publish, right? Therefore, first you have to think about accuracy of your prepared hydrochloric sample. So how do you, if you standardize this one, you have to titrate this 0.02 m HCl with 0.02 m sodium hydroxide, right? So you have to use the 0.02 m sodium hydroxide 1:1 ratio. Phenolphthalein you can use as an indicator. Then you can standardize the hydrochloric acid, right? Once you standardize it, now everything's ready. You have 0.02 m HCl indicator and 4% boric acid, right? Now you can start the distillation unit, right? Then you can trap the 4% boric ammonia in 4% boric, right? Then you have to fill the 0.02 m HCl into the burette. HCl into the burette, and we are going to titrate ammonia within the boric acid with HCl, right, using mixed gel-dahl indicator. Right. Before that, if you use boric acid, right, you have to add indicator to that. Right? When you mix the boric acid solution to the distillation unit, you have to add few drops of indicator. Right? Initially, without ammonia, you can obtain nice blue color. Without ammonia, dark blue color, nice blue color. Right? If the sample contains nitrogen, it can form ammonia. Right? When ammonia reaches to the system, then the medium convert into basic. You can observe apple green color. You can observe apple green color. So this technique you can use before the analysis. Once you prepare the indicator, whether it is work or not. If you really need to check whether your indicator is work or not. How do you check it? Take ammonium hydroxide available in the sample and mix it with small few drops of indicator. If the indicator changes its color into apple green with ammonia, that is okay. Then you can add few drops of HCl. Right? Then again indicator change back to the normal color. Right? You can check the indicator like that. You can check the indicator whether it is work or not. Right? Right. Then you have boric acid with indicator, that is dark one, dark blue one. When you distill off the ammonia mixed with the boric acid, then the color becomes apple green. So apple green sample, now we are going to titrate with 0.02 mHCl. 0.02 mHCl. What will happen? At the end point, when HCl interact with ammonia, right, you can observe the reaction by the color change of the indicator. At the last drop of HCl interact with ammonia, the next drop of HCl convert the indicator color into the blue color, right? Blue color. When all the ammonia interact with the HCl, the next drop of the HCl convert the indicator into its original position. Then you have to take the reading of this burette reading. You have to take, right, and calculate the amount of nitrogen available in your sample. Amount of nitrogen available in your sample, right? Right. Before that, now this is the titration part, right? Before I go for the calculation part, I would like to explain the certain chemical reactions involved in this analysis. Certain chemical reactions involved in this analysis, right? First one, nitrogen in the sample. Nitrogen in sample. When you interact with the sulfuric, convert into ammonium sulfate. This is the first reaction. Ammonium sulfate. This is the first reaction. Then this ammonium sulfate distillation level, ammonium sulfate interact with the sodium hydroxide. Two sodium hydroxide. Product is the sodium sulfate plus 2 ammonia gas plus 2 H2O plus ammonium hydroxide. Right. Third reaction, this is first, this is second. Third reaction, boric acid. Boric acid means this kind of acid. This is trap the ammonia, not interaction. Boric acid trap the ammonia. Right? Then last reaction, you can write down very easily. Ammonia with this ammonia plus HCl. Ammonium ion plus ammonium ion plus chloride plus water. Ammonium ion with ammonium chloride. Right. So 1-to-1 ratio. 1-to-1 ratio. Right. So the calculation part. Percentage of nitrogen of your sample percentage of nitrogen of your sample. The burette reading is V, right? Concentration of 0.02, right? Divided by sample weight W. Number of moles we can convert into grams because of the nitrogen. Then 100. Is the percentage of nitrogen available in the sample. Right? So if we think about this value, V value, right? So you cannot confirm medium does not contain nitrogen. When you do the experiment, you cannot confirm medium does not contain nitrogen. So how do you correct that part? To do it, you have to analyze the same, at the same time you have to maintain the black analysis. Black analysis means without sample, you have to digest the other parts, right? Without sample, right? If there is a reading, you have to deduct that reading from the original one. That is the correction, right? This V may be corrected reading. Corrected reading. If there is a reading for the blank one, you have to deduct that reading from the final analysis, right? If the deducted reading is B into 0.002, that is the concentration of the HCl divided by sample weight into 1014 into 100% as a percentage, right? This is the nitrogen percentage. Now, how do you convert this into protein? So when you come to the protein level of the sample, right, we have to multiply this by magic number or factor. Magic number or factor, right? So this magic number, right, from food items to food item, magic number can be changed. From milk, magic number like 5 point like values, right? For meat, magic number is 6.25. Vegetables, certain numbers. Wheat flour, certain numbers. So you have to find the relevant magic number, relevant factor for this. Average one, magic number. Average number is 6.25. 6.25. Therefore, percentage of protein equals V into 0.002 divided by 1000. 1000 into 14 into 6.25 into 100. So this is the percentage of protein available in the sample. Right? Now, when you think about this analysis, this contains so many errors with its starting point. Right? When you take the weight, there can be error. Right? Then digestion step, depending on the indicator, there can be error. Recovery level, there can be error. Right? Distillation rate, there can be error. Right? And finally, titration. Titration can be personal errors like this. Right? So whole process contain more errors. Right? So finally, we cannot directly determine the protein. That is another error. We can determine the nitrogen percentage using this technique, right? So we have to use another artificial numbers, right? That means this is a calculated one. This is not an experimental one. Experimental up to this level, nitrogen percentage. Right? Then we have to use special factors to calculate the thing, right? So if we think about the whole process, right, there are a number of errors involved in this process. Therefore, when you use Geldal technique to evaluate the protein content of the food material, right, you have to be very careful. Because if you use only this method to evaluate the protein content, you will be in a trouble. Right? So this is the Geldal technique. So there are so many other accurate methods. Directly you can analyze the protein content of your sample. This is the Geldal method. Then we will see what are the other methods available for the protein analysis. Other methods available for the protein analysis. Right? Before that, I have to say one thing. When you use sample for the Geldar method, when you use sample for the Geldar method, if the sample contain more fat, right, you can observe this kind of thing. If the sample contain more fat, there is a Geldar tube, there is a sample, certain fatty material try to go up and contact with the surface of the internal surface of the tube. Therefore, the best way is please remove the fat and moisture from the sample before you use the sample for the Geldal analysis. The best way is removal of the fat and moisture before you start the analysis of the sample for the protein using Geldal method. Right. Then we will see another technique, direct analysis for protein. Right. Direct analysis of protein. That is 4 mole titrate. 4 mole titrate. 4 mole titrate. Right. Here we use amino acid like this. NH2. Right. This is the amino acid. Right. We have to add formaldehyde to this amino acid. When you add formaldehyde to the amino acid, formaldehyde can block the amine end of the amino acid like this. H. This end is available. Right? But amine end blocked by the formaldehyde. Right? This group is known as methylene immunogroup. Methylene immunogroup. Right? If I repeat it again, you have to take the sample and add formaldehyde as a blocking agent, because if you go for the titration, direct titration, there are 2 active positions, amine and carboxylic position. We have to block one of these one. Using formaldehyde, you can block amine end. Right? Blocking part is the methylene immunogroup. Now, carboxylic part is available for the titration. Right? Carboxylic part is available for the titration. Any base you can use. Right? Any base you can use. Right? You can titrate with the sodium hydroxide like this. Then 1:1 ratio, you can directly say the amount of protein. Right? Not like Geldar method. Not like Geldar method. No need to correction like factors like this. Correctly, you can calculate the protein content of your sample. That is the second method. Right? Right. Then we will see third method. Third method is a dye binding method. Dye binding method. Dye binding. Here we are going to use azo dyes. as a main reagent. SO dyes as a main reagent. Right? First, we have to measure the intensity of the dye solution using colorimeter. Intensity. Initial intensity we have to measure. Right? Then you have to mix the known amount of this sample with the dye. You have to mix known amount of sample with the dye. So what will happen? What will happen? Most probably, protein amino acid molecule absorb the dye pollution. So most of the dyes are anionic dyes. Most of the dyes are anionic. So if we take protein has two ends, COO minus and NH3 plus, two ends. Right? So anionic dye always try to form bonds with the NH3 plus end. That means certain amount of dye attached with the protein molecule like this. Right? So after this experiment, again we have to check the intensity of the dye solution. Right? Intensity of the dye solution. So theory is absorption is proportional to 1 over amount of protein. Why? When protein content increase, absorption, right? Absorption of the dye decrease. Absorbance, not the absorption, absorbance decrease. Initial absorbance very high, right? When you mix it with protein, what will happen? The part of the dye absorbed by the protein molecule because of its anionic nature. Anionic nature. Right? Right? Then we have to think about the absorbance after mixing with the sample. Absorbance decrease if the protein content is increased. Then you can directly, based on the Beer-Lambert law, you can directly calculate the protein content within a short period of time. Right? The main thing is, before the analysis, you have to standardize the data. That is the main point. Right? That is the third thing. So fourth one, same as this one, that is again colorimetric one, ninhydrin test. You know ninhydrin can form complex with the protein. Ninhydrin can form complex with the protein. So those complexes are colored complexes. Ninhydrin can form complex with the protein. Those complexes are colored complex. So once we obtain colored complex, what we can do, we can measure the absorbance. Again, using standard curve, calibration curve, right? With the known quantities of protein with ninhydrin, right? I think you know the technique because we have already discussed how to use colorimetric techniques for the analysis. If you try to use colorimetric technique for the analysis, always we have to prepare the calibration curve with the known quantities, right? Then you can analyze unknown sample with the calibration curve, right? Again, colorimetric technique, ninhydrin test, analyze only the protein available in the sample, not the nitrogen. Protein can form complex with ninhydrin, not the nitrogen, right? So out of all four techniques, that means gel dye, formol, dye binding, and ninhydrin, last three one, except gel dye, directly analyze the protein content available in your sample. First technique, gel dye method, cannot use to analyze protein content directly, right? Directly evaluate nitrogen content available in the sample, right? So that is, these are the important points of the protein analysis. With that, we can complete the proximate part of the analysis. Now we can move to the analysis of carbohydrate. Actually, we are going to analyze reducing sugars. To analyze the reducing sugar, there are different techniques. Right? Now we are going to use modified Lane and Enel method. Modified Lane and Enel method. Right? To analyze the carbohydrate or reducing sugar available in the sample, right? We can use different techniques. Here we are going to discuss about the widely used technique, that is modified Lane and Enel method. Right? Here the sample preparation of the analysis is very important. You have to prepare the sample through the dilution series. Like this. Right? First we have to take the 5 gram of sample. And dissolve in dissolution. Dissolve in 250 ml of water. Right? 250 ml. Dilute up 250 ml. Then take 50 ml. Take 50 ml from this 250 ml and dilute it up to 200 ml. And you can take 25 milliliters from the diluted one for the analysis. Right? Now you can check. The sample volume like this. Right? First, we have to take the 5 gram. And take the 5 gram. Right? And dissolve it into 200 up to the 250 ml using volumetric glass. And using pipette, you can take 50 ml from this 250 ml solution, and you have to dilute it up to 200 ml. Right? Then you have to take 25 ml of the sample for the analysis. Right? You have to fill this 25 ml into the burette. Now sugar solution into the burette. Right? Then you have to measure failing A and B mixture. Failing A and B. 20 milliliter each. We have to prepare the mixture. Failing A and B solution. Right? After mixing, you have to add 15 ml of water. 15 ml of water. Right? And you have to put the sample failing mixture, failing A and B. Right? Then water. Right? Then you have to add 1% methylene to it. 1% methylene. few drops. Right. Now we have water, failing A and B, methylene blue, right? Now we are going to boil this mixture, therefore we have to add few amount of anti-bumping fumes, humidity stops, anti-bumping. Right? Now we are going to boil the mixture. Boiling. By using direct flame, we can boil it. While boiling, you can add dropwise sugar solution to this system. Right? When you add sugar solution to the failing A and B mixture while boiling, right? You can observe time to time. You can observe convert the sugar failing A and B mixture into the red color, but not the permanent. Dropwise, when you do the titration, you can observe the formation of red color time to time within the beaker. Right? But after 1 or 2 minutes, just when you add the sugar solution, right, 1 or 2 minutes, then you can observe permanent brick red color formation, that is the endpoint. Right? Permanent brick red color formation within the beaker, that is the endpoint. You have to stop the titration. Right? You have to stop the titration. Right? Now this is not the sample. This is sugar. You have to take 5 grams and prepare the 25 milliliter of sample using that 5 grams. Right? So you have to prepare the failings A and B. Now with this system, we can standardize our failing solution. How many milliliters required to obtain this one? How many milliliters required to obtain this one? Right? Or in other ways you can do. In other way you can do. Right? Other way mean you can use reducing sugar tables. Reducing sugar tables for the calculation. Right? So this is the easiest way. You can use this one, this experiment as the calibration. Right? Calibration. Under this condition, sometimes you may need 15 milliliter of sugar. 15 milliliter of sugar. Right? 15 milliliter of sugar for this one. Right? Turn into brick red color. Right? Right. Then 15 milliliter you can calculate the amount of sugar in the sample. Right? Then you can calibrate like this, known amount of sugar required 1. Right? Then you can easily calculate the unknown sample. Right? Right. So why do we add methylene blue? Why do we add methylene blue? Methylene blue is not to identify the pH change. That is not to identify the pH change. Right? Methylene blue used to clear the solution to identify the brick red color. Without methylene blue, you cannot observe clear brick red color. Clear brick red color in the solution. Right? Therefore, we can use methylene blue to clear the solution, to clear the clear observation of brick red color. Not only that, when you do the experiment, you have to complete the experiment within 2 to 3 minutes. Do not go beyond 3 minutes. Why? This is a reducing reaction. That means failing A and B undergo reduction. In addition to sugar, sometimes certain molecules, certain reducing molecules join with the failings A and B. Join with the failings A and B. Then it will reduce. But we may think that reduction is due to the sugar solution. Therefore, you have to complete this titration within 3 minutes, maximum 3 minutes. Don't use extra time for the analysis. Right? Right. Sometimes when you try to analyze this one, right? When you try to analyze this one, within 1 or 2 drops, you can obtain the endpoint. 1 or 2 drops, you can obtain the endpoint. So, with that kind of sugar solution, you cannot go forward. Why? It indicates your standard sugar solution is too concentrated when compared to the Paley's mixture. When compared to the Paley's mixture, your standard sugar solution is too concentrated. Right? So, you have to dilute it. Sometimes you cannot obtain endpoint although you add all the amount of sugar from the butyrate. What does it mean? It means your sugar solution is too dilute. Your sugar solution is too dilute. That means you have to increase the concentration of your sugar solution. Increase the concentration of your sugar solution. Right? Right. Then you can easily calculate the sugar content directly. Right? In addition to this way, you can use the same analysis like this. Right? Sometimes in the laboratory, you can do this analysis like this way. You have to fill the valence mixture. Valence A plus B to the butyrate. And the sugar solution to this sugar. To the B. This is another way. Right? And again, you have to add methylene to anti-bounding agent and you have to boil. Right? With non-sugar concentration, you have to standardize the fading A and B like this. Right? Like this. Once you standardize the valence A and B like this, now you know the amount of valence A and B required for the sugar solution. That means you can plot a graph with the non-concentration, right? Non-concentration of sugar. Sugar concentration, right? This is reading. Purine reading. That is fading A and B. Right? Then, if you introduce the unknown one, to the mixture, now you can have reading for the unknown one, and directly you can say percentage of reducing sugar available in the sample. That is the another way. There are few ways, right? First way like this, second way like this, third way, very old method, you can use reducing sugar tables. Reducing sugar tables. Right? Once you determine the reducing sugar, you can convert this into percentage of sucrose. Percentage of sucrose is equal to reducing sugar percentage multiplied by 0.95. When you multiply this reading by 0.95, now you will end up with percentage of sucrose. Percentage of sucrose available in the sample. Right? So we are going to start the new section, that is preservatives. How to analyze preservatives. Here we are going to discuss selected preservatives, not all the preservatives available in food acts, right? But widely used preservatives we are going to discuss under this session, right? First of all, if we think about SMS, SMS means sodium metabisulfite. Sodium metabisulfite. Chemical formula Na2H2O5. Right? Na2H2O5. So activity of this chemical list in the presence of acid, this can create two sulfur dioxide molecules. One sodium metabisulfite molecule in the presence of acid can release two sulfur dioxide units. Right? So actual active form of the SMS is a sulfur dioxide because sulfur dioxide can preserve the food. Sulfur dioxide can preserve the food. Right? Now we are going to learn how do we analyze SMS content or sodium metabisulfite content available in our food material. Right? So first of all, we will think about the qualitative measures. How do we qualitatively analyze the SMS content? So to do it, we need conical flask, right? Conical flask, and we need condenser, right? Conical flask and condenser. We have fixed the condenser, the conical flask, the body, the water inlet and outlet, right? And we are going to place the sample here. Right? We are going to place a sample inside the conical flask. Right? So now we need to create sulfur dioxide, right, within this system. To release sulfur dioxide, if the sodium metabisulfite available in the system, right, we need to add acid. That means generally we use hydrochloric acid. Right? Hydrochloric acid. Right? Then you can release the sulfur dioxide. That is okay. Things are okay. But the problem is, right, how do we identify the sulfur dioxide qualitative? Right? How do we identify the sulfur dioxide qualitative? To do it, we can practice several techniques. Right? One is we can practice the piece of paper. Actually, this is a filter paper, right? With potassium dichromate, A2Cr2O7. Right? That means take the potassium dichromate solution, dip the piece of filter paper in the potassium dichromate solution. Now you will have potassium dichromate containing filter paper. Or you can have preparation of the piece of filter paper with lead chloride. Lead chloride. Right? So that means take the lead chloride solution and dip the piece of filter paper like this into lead chloride solution. Right? Now it is lead chloride containing paper. Right? Filter paper. Right? Then if you use one of these filter papers for the identification, what will happen? When sulfur dioxide interact with the potassium dichromate. Potassium dichromate containing paper is a color is a orange color. Color is a orange. This is colorless. Original color is colorless. So when this exposed to sulfur dioxide, right, this dichromate can form chromic ion. Right? This is green color. Right? This is green color. That means when sulfur dioxide interact with the dichromate, right, it can turn the color of the dichromate paper from orange to green. from orange to green. Once you observe the color change, now you can say there is a sulfur dioxide. Right? So if you use lead chloride, it is a colorless. When it interacts with the sulfur dioxide, what will happen? Formation of lead sulfide. That is a black color. Right? That's a black color. So if you use lead chloride as indicating a reagent, it can form black color lead sulfide with sulfur dioxide. That means if you observe black color change into colorless to black color, that means you can think yes, sample contain sulfur dioxide. So that is the indication system. Right. The other one important point is generally we apply SMS like preservatives in ppm level, parts per million level, not milligram or grams level. Very minute quantities we are going to apply. For example, if we think about the cordial, 300 ppm maximum allowable level. Right? If we think about the fruit juice, maximum allowable fruit juice means ready to serve fruit juice, maximum allowable one is 72 ppm. That means 1 kilogram of that food material contains 72 milligram. Very minute quantity. Right? With that very minute quantity, if you try to analyze it qualitatively, it is not easier one. Because when you add HCl, it can interact with the very minute quantity of the sulfur dioxide. SMS, it will release very minute amount of sulfur dioxide. Right? This amount is not enough to go up to this level. Reacted sulfur dioxide amount not enough to go up to the top end of the distillation unit. Right? So what we have to do? Anyway, you have to bring up this sulfur dioxide up to this level. So we have to practice very small technique for that. That means along with the sample, we have to add calcium carbonate. Along with our sample, we have to add calcium carbonate. Right? Then we can boil. Now we have calcium carbonate, sample plus HCl. You know, when you add calcium carbonate, HCl interact with the calcium carbonate also. It can release carbon dioxide, large quantity of carbon dioxide. So that carbon dioxide can mix with the sulfur dioxide. It can very easily move up to the level. But the problem you may have, now there are two gases now. How carbon dioxide interact with the dichromate and lead chloride, right? No, that is not a big problem, right? Because carbon dioxide can move up to this kind of level, not up to this level. Why? Carbon dioxide is a condensable gas. Condensable gas. It is a condensable gas. Therefore, when you cool it, it can come back to the conical glass. But after this level, sulfur dioxide cannot come back. It can go up to this level because sulfur dioxide is not a condensable, that is non-condensable gas. Sulfur dioxide is a non-condensable gas, right? We can take the help of carbon dioxide to bring the sulfur dioxide up to this level, right? So sulfur dioxide cannot bring back, right? Come back to the original position. When it comes up to this level, it can try to move up, right? Then you can very easily identify sulfur dioxide qualitatively, not quantitatively. Right? Right. Then we will see how do we analyze the sulfur dioxide quantitatively. That is very important. We are going to discuss two techniques for that. Analysis of sulfur dioxide quantitatively. Right. First technique is distillation and titration method. Distillation and titration method. So these are the apparatus we can use. First you need double neck glass, right? double neck glass, right? Then one neck of the glass connected with the tubes like this. One neck of the glass connected with this kind. Then this is connected with the condenser. Then we have to use the beaker, and at the same time we have to prepare the burette for the titration. Burette for the titration. We have to set the burette, right? Now water inlet, water outlet, right? Other end joined with the special glassware, that is the separative funnel. Separative funnel, right? We have to fill the separative funnel. So if I draw it clearly, right? So we have to fix the separative funnel here. Right? We have to fill the separative funnel with HCl. HCl. Then we have to supply the heating source, burner like this. Right? Before the analysis, we have to fill the burette with 0.05 N iodine solution. Before the analysis, we have to fill our burette with 0.05 N iodine. And before the analysis, we have to add distilled water. Right? Distilled water, that is around 150 milliliters. Distilled water to the liquid. Right? Then what we have to do is, before the analysis, we have to add 0.5 ml of 0.505 N iodine to the solution. Before you start the analysis, what you have to do is, you have to use in this burette, you have to add 0.5, not 1 ml, 0.5 ml of 0.5 N iodine from this solution to the beaker, right? In the meantime, you have to add 1% starch solution. Few drops of 1% starch solution. So what is the color? What could be the color? Now iodine is there, very small amount, and starch is there. Now you can observe blue color in the beaker. Blue color in the beaker. Then what we have to do, we have to release the hydrochloric to the double neck glass. So double neck glass contains sample. So once you release the HCl, so what will happen? When you boil the mixture, if the sample contains sulfur dioxide, so that sulfur dioxide, SMS, that SMS creates sulfur dioxide and go through these tubes and easily mix with the beaker solution. Right? Now sulfur dioxide mixed with the beaker solution. Now beaker solution contains iodine. Right? So iodine converted into iodine. Right? Iodine converted into iodine. Right? When sulfur dioxide interact with the iodine available in the solution, it converts into iodine, reduce some of the iodine. So what will happen to the color? When iodine converted, with iodine mixed with the starch, blue color. But iodine cannot give the blue color. Therefore, if iodine convert into iodide, this beaker color change into colorless form. This change into colorless form. Right? Then what you have to do? Dropwise, you have to add the 0.05 iodine to the beaker from the burette. Right? Once you observe the colorless, then add few drops. Then you can observe again blue color. Then due to the sulfur dioxide, that blue color disappears. Then add few drops of 0.05 iodine. Likewise, right, until all the sulfur dioxide released from the sample, you have to do this exercise. Right? If all the sulfur dioxide released, right, then there are no sulfur dioxide from this cell. Right? Therefore, when you add the 0.05 iodine to the solution, in the absence of sulfur dioxide, again you can observe blue color because of the starch solution. That is the end point. Starting point is blue color due to addition of 0.5 ml of 0.05 iodine. Right? Then we add 1% starch solution. Starting point is blue color. Then we start the reaction. Sulfur dioxide interact with the iodine. It can convert iodine into iodine. Sulfur dioxide. Right? So what will happen when iodine converted to iodide? Blue color disappear and solution color become colorless. Once you observe the colorless solution, then you can add few drops of iodine solution from the burette. Then again you can observe blue color. And continuously sulfur dioxide come into the solution. All the sulfur dioxide convert iodine into iodide. When all the sulfur dioxide evolve, right, then there are no more sulfur dioxide from this side. What will happen? Then what will happen? These iodine interact with the starch solution. Again, we can observe blue color. That is the end point of the reaction. Right? Then we will think about the calculation part. For this analysis. Generally, 1 ml of this is the assumption 0.05 N iodine is equivalent to 0.0016 grams of sulfur. So this is the theory. This theory you should know before the calculation. 1 ml of 0.05 N iodine equals to 0.0016 grams of sulfur dioxide. Then you have to calculate the titration volume. It is titration volume is simple V ml, right? What is the real volume? V minus 0.5. At the very beginning, we add 0.5 ml from the burette. At the very beginning, we add 0.5 milliliters from the beginning. Therefore, corrected volume, required volume for the titration is V minus 0.5 ml. Now, sulfur dioxide content, that is sulfur dioxide content equals to 0.0016 into V minus 0.5, right, divided by W means sample weight of the sample. So that is in that. But generally, for the preservatives, we cannot express this value as a grams, because always we are going to use the preservatives in ppm level. Therefore, we have to multiply this by 10 to the power 6. Right? That means finally SO2 content in ppm equals 0.0016 divided by W into V minus 0.5 into the 10 to the power 6. Now this is in pp. This is in pp. That is one method. One quantitative method you can use to analyze the sulfur content. One quantitative method you can use to analyze the sulfur content of your sample. Right? Then we can think about another method, second method. Right? Calculation part is same. Calculation part is same, but method is little bit different. Same meaning. Calculation part is in ppm level we have to calculate. Right? Here we are going to use hydrogen peroxide. Okay. So this is the setup. First you have to select the research system. You have to put the sample here. Right. Source. Then you can generate the sulfur dioxide with acid. Then send the sulfur dioxide into one UT. Right. This U-tube contains hydrogen peroxide. Right. Then again you have to bring the resultant one. Then again you have to send it to the U-tube. This one also contains hydrogen peroxide. Then you have to collect the product. Right. So here we are going to generate the sulfur dioxide using the normal traditional system, that is interaction with sample with HCl. So that means this should contain HCl. Right. Then sulfur dioxide bubble to the hydrogen peroxide, H2O. So what will happen? Production is sulfuric acid. Production is sulfuric acid. Right. Then we have to take the product into the titration flask, right? And titrate. Now this is the sulfuric acid, therefore we have to use sodium hydroxide for the titration. Sodium hydroxide for titration. So sulfuric acid interact with the sodium hydroxide. The product is sodium sulfate plus water. Right? With the OH. So ratio between sulfuric to one is 1 to 2, right? This is 1 to 1 ratio, right? Now you can analyze. Sulfur dioxide content in your sample quantity based on this stoichiometric relationship. So these are the methods available for the determination of sulfur dioxide. Then we will move to the next preservative, that is sodium nitrate, sodium nitrite. sodium nitrate, sodium nitrite. The next preservative, nitrate and nitrite. This is the next preservative we are going to study. Generally, nitrate, nitrite used in meat industry due to three objectives. Right? Nitrate, nitrite widely used in meat industry, three objectives. So actually, manufacturers expect to fulfill three objectives by using nitrate, nitrite. First objective is a preservation. You know it, right? So by using nitrate, nitrite, you can preserve the meat products for a certain period of time. Can control the Clostridium botulinum population. That is the basic thing. The second one, color formation. Right? Nitrate, nitrate can form very nice color within the food. Third one, flavor formation. It can add very good, high standard flavor to the product. So role of the nitrate, nitrite. So we can discuss under all three categories: preservative action, color forming action, and flavor generation action. Right? So anyway, under this course unit, we are not going to discuss about the activity of nitrate, nitrite. That is, you have to discuss under preservation lecture, right? But instead of that, we are going to explain how to analyze nitrate and nitrite content available in the food material. To analyze the nitrate and nitrite, so we are going to use special Amos reaction. That is, by using colorimetric measurement, we can analyze the nitrate and nitrite. So that reaction is known as Illos reaction. Illos reaction. Illos reaction we are going to use to analyze the nitrate and nitrite content. Actually, this is nitrite content we are going to analyze, not nitrate. All the nitrate in the sample within the analytical system, we are going to convert into nitrite by using certain reagent. So that means we need to prepare the set of reagent, right, for the Illos reaction before start the analysis. So I will give the set of reagent, right? I will give the set of reagent from 1 to 6, right? Now you can write down the reagent, right, with their number. When I discuss the extraction and confirmation part of the Illos reaction, right, I use those numbers, right? At that point, I am not going to give the, I do not like to give the details of the reagent. Details I am going to do here, right? So reagent number 1, how to prepare the reagent. Reagents for the reaction. Reagent number 1. So you have to dissolve 106 grams of potassium peroxide. 106 grams of potassium peroxide. Potassium peroxide. In water and dilute up to 1 liter using water. That is the first reagent. Reagent number 1, 106 grams of potassium peroxide in water and dilute up to 1 liter. Right? Then reagent number 2. Then you dissolve 220 grams of zinc acetate. Zinc acetate. Dihydrate. Zinc acetate dihydrate, right, in water right, and you have to add 30 ml of glacial acetic acid. Glacial, which is, and dilute up to 1 liter. That is again, you have to use the water for the dilution. Right. Then reagent number 3. Reagent number 3. Dissolve 50 gram of 50 gram disodium tetraborate decahydrate. Disodium tetraborate decahydrate. Disodium tetraborate decahydrate, right, in 1 ml of water. In 1 ml of water. Reagent number 4. Then dissolve 2 grams of sulfanylamide. Is the reagent sulfanylamide in 80 milliliters of warm water. Right? And add 100 ml of concentrated HCl and dilute up to 1 ml. Dilute up to 1 ml. Right? That means fourth reagent is 2 gram of sulfanylamide in 80 milliliter of warm water and add 100 ml of pump HCl and dilute up to 1 liter again with water. Right? Then reagent number 5. So I use this space for that. Reagent number 5. Reagent number 5. Dissolve 0.25 grams of 0.25 grams. 0.25 grams of N-naphthalene diamine dihydrochloride. This is the reagent. N-naphthalene diamine dihydrochloride. Reagent is N-naphthalene diamine dihydrochloride. In water, dissolve this in water. Right? Right? Then dilute. Dilute in the 1 liter using water. Then sixth reagent. We have to dilute 445 ml of HCl to 1 liter. You have to dilute 445 ml of conc HCl up to 1 liter using water. So these are the major reagents what we are going to use to analyze nitrate and nitrite content available in your sample when you use the Illosley reaction. Right? Basically, Illosley reaction, we are going to convert all the nitrate available in your sample using nitrite, right? Using this set of reagents. So first reagent, if I repeat it again, first reagent number 1, 106 grams of potassium ferrocyanide in water and dilute up to 1 liter. The second reagent, 220 grams of zinc acetate dihydrate in water plus you have to add 30 ml of glacial acetic acid to it and dilute up to 1 liter with water. Third reagent, 50 grams of disodium tetramonate decahydrate in 1 liter of water. Reagent number 4, 2 grams of sulfanylamide in 80 ml of warm water and add 100 ml of foam HCl and dilute up to 1 liter. So reagent number 5, 0.25 grams of N-naphthalene dihydrochloride in water and dilute up to 1 liter. Right. The sixth reagent, 445 ml of foam HCl, dilute up to 1 liter. So these are the major reagent what we are going to use in Illousway reaction. Right. In addition to that, we have to prepare the stock solution of sodium nitrite because we are going to colorimetric assessment. Therefore, we have to prepare the stock solution for the calibration curve. For the calibration curve, we need stock solution, right? So standard solution, right? For the standard solution of the sodium nitrite, so this is the standard solution. First, we have to take 1 gram of sodium nitrite in water, right? Then we have to dilute up to 100 ml. Using this 100 ml, you can prepare different solutions, right? And you can prepare the calibration curve, right? Absorption, concentration, right? With this stock solution, right? With this stock solution, right? So the Illousway reaction consists of 2 phases. Illousway reactions consist of 2 phases, phase 1 and phase 2. Right? First, you have to think about the phase 1, and phase 1 is actually preparation of your sample for color measurement. That is actually sample extraction process. Then the phase 2 is color measurement, colorimetric measurement. So that is the important points of the Illousway reaction. Then you have to perform your reaction according to the phase 1 and phase 2 steps. Right. So if I take the step of the experiment, first we have to take 10 gram of the sample and transfer it to 100 ml beaker. 100 ml beaker and add 5 ml of reagent 3 and 70 ml of hot water. Right? Then transfer the content into 200 ml of calibrated flask. This flask is very important, calibrated one. 200 ml calibrated flask. Calibrated flask. Right? Then add 70 ml of hot distilled water. No reagent. Hot water. Right? Then you have to heat. Next step is heat. Then cool. After heating, you have to cool it. And next step, you have to add 2.00 ml. You have to use the pipette of reagent 1 and 2.00 ml reagent 2. Right? How many milliliters available in this one? Right? Here 75 milliliters. 70 plus 5. Right? Then additional 70. 145. Right? Now 4. 149, almost 150. That means to fill this vessel, we have to add 54 milliliters, 52 milliliters of water, distilled water. Right? That means you have to add distilled water up to the mark. Distilled water. That is 52 around. Now it contains 200 milliliters. Right? Then you have to adjust the pH. Adjust the pH up to 8.2. You have to do the pH adjustment using pH meter up to 8.2. Then stand for the precipitation for 30 minutes. Stand for 30 minutes. Then carefully filter the super, not the other one, super, through nitrate, nitrite free filter papers. Free filter papers. So this is the phase 1 of this experiment. Extraction of the nitrate, nitrite into the medium. Right? If I repeat it again, 10 gram of sample you have to obtain. 10 gram of sample. Then if you take 10 gram of sample, you can transfer it to the 100 ml of beaker and add 5 ml of reagent 3. Now you know what is reagent 3, right? And 70 ml of hot water. Then transfer all material into 200 ml calibrated vessel, beaker. Calibrated means it should be calibrated, right? And add 70 ml of hot water again. Then we have to heat the system and cool the system. After cooling, we can add 2.00 ml of reagent 1 and 2.00 ml of reagent 2. Now you know what is reagent 1 and reagent 2. Reagent 1 is actually potassium ferrocyanide, reagent 2 is zinc acetate. Right? You should know what are the reagents. Then adjust the pH up to 8.2. You can use sodium hydroxide of HCl for that. Right? Then stand for 30 minutes. Right? After settle, you have to filter the supernatant through nitrate, nitrite free filter paper. That is phase 1. Phase 1. Right? Then we will see phase 2 of this analysis. Phase 2 of this analysis. Phase 2 is a color measurement. Phase 2 is a color measurement. Right? Then you have to take V milliliter of the extract, VML. Once you prepare the extract, V milliliter of the extract you have to take. Then you have to add 60 ml of distilled water. Distilled water to the V milliliter of the extract. Then you have to add 10 ml of reagent 4 and 6 ml of reagent 6. Now you should know what is reagent 4, what is reagent 6. Then you have to keep the mixture in dark. In dark environment. That is about 3 minutes. You have to keep the mixture. Then dilute the mixture up to the mark. Dilute up to the mark. What is mark? So if we take this V milliliter in 100 ml plus now at 60 plus V, then 16 60 plus V. The rest of the amount you can dilute using distilled water, right? Then sorry, that is after this one, not dilution, that is wrong. After this one, after keeping the sample in dark, you have to add 2 ml. 2 ml of reagent 5. Again, leave for about 3 minutes in dark. Then you can dilute up to the mouth. Dilute up to the mouth. Then you can use this sample to measure the absorbance. Colorimetric method. Right? Before that, you have to do the experiment without sample for calibration curve. Calibration curve. Once you develop the calibration curve for the nitrite, right? Now, based on the reading of absorbance of this sample, now you can directly say the concentration of nitrite available in the sample. Here, role of the zinc acetate is conversion of all nitrate into nitrite, because in this technique we are going to evaluate nitrite, not the nitrate. Therefore, to convert the nitrate into nitrite, we have to add zinc. Role of the zinc acetate like that. Right? So whole general reaction we can simplify like this. Whole general reaction we can simplify it like this. We can simplify it like this. Nitrite is so like that. Convert into resultant compound, that is we can impact sulfanylide, sulfanylic acid, right? Then compound we can observe. Then we can mix with the naphthylamine. If you take the numbers of the reagent, naphthylamine, then you can observe the azodite, right? Then measure the absorbance. So this is the simple reaction of this determination. First, we have to convert all the nitrate into nitrite using zinc. Then, anyway, we have to interact the sulfanylic acid diazotization. The reaction, formation of diazonium salt. Right, active compound is a diazonium salt. Then diazonium salt interact with the naphthylamine, right, and form azodite. That is the chemistry behind this analysis, right? Then we are going to measure the absorbance of this azodite. Right? Right. That is about the nitrate and nitrite. Now we can think about the formalin in fish. Formalin in fish. Formalin Formalin means 40% formaldehyde. Formalin means 40% formaldehyde. Before we analyze, we have to extract the sample using this way. Right? First round bottom glass. We have to use the tubes. First class is an actual steam generator. Right? Second class contains sample. Right? This is steam generator. Steam generator. This consists of water. When you boil water, steam generated. Generated steam, they boil the sample here. When the sample contains formaldehyde, 40% formaldehyde, it can release and come to this one. So this one contains formaldehyde. We can collect formaldehyde like this. Right? This is a sample extraction technique. Sample extraction technique. Right? Once you prepare the formaldehyde sample, then you have to take 1 milliliter of the sample, 1 milliliter of the sample extract. Then you have to add 0.2 ml of chromatotropic acid. This is the name. Chromatotropic acid. Complex forming acid. This can form complex with formaldehyde. 2 chromatotropic acid form joined with 1 formaldehyde. 2 chromatotropic acid joined with 1 formaldehyde urine. Right? Then to help for the connection of this complex, we have to add 4.00 ml of sulfuric acid. Then we have to boil the mixture. Boiling. After boiling, we can measure the absorbance. Right? Very simple technique. First thing is you have to extract the sample, right? Steam distillation unit. Then second thing, we have to take the extract at least 1 milliliter, then mixed with complex forming acid, that is chromatotropic acid. This can form color complex with formaldehyde. 1 formaldehyde unit interact with 2 chromatotropic acid unit. Then you have to add 4.00 ml of sulfuric. This is not a 400. 4.00 ml of sulfuric. Then you have to boil it. And measure the absorbance. Right? Then you have to prepare the series of known concentration of chromatotropic acid for the calibration curve. Now you can, with the help of that calibration curve, you can determine the formaldehyde content or formalin content available in your sample. That is formalin. Then we will move to the next preservative. That is benzoic acid. Benzoic acid. Right? First, we have to take the sample. Take the sample and interact with dilute sulfuric acid, right, and sodium chloride. Right. Take the sample and interact with dilute sulfuric and sodium chloride. The role of the sodium chloride here, right? Role of the sodium chloride here is extractability, increase the extractability of the benzoate, because benzoic acid available in the sample as the benzoate, not the benzoic acid. So this is the benzoic acid now. This is benzoic acid. COOH. But generally, this is available in the sample as this COONA. This is the polar one. That's why benzoate soluble in water. Right? Now, from this step, we are going to check. We are going to convert benzoate into benzoic acid. Benzoate into benzoic acid. That's why we add dilute sulfate. And with the help of sodium chloride, we are going to extract benzoic acid into ether. Why do we use ether? Once you convert this into benzoate converted to benzoic using sulfuric, now it is no longer polar, not easily dissolved, but it is more like to dissolve in ether. Therefore, we are going to transfer the benzoic organic acid into the ether layer. Right? Efficiency of extraction increased by sodium chloride. Right? Then we are going to introduce sodium hydroxide. Sodium hydroxide. Now we have alkaline solution. Little bit alkaline solution here. Right? To this alkaline solution, we have at first reagent potassium permanganate, KMnO4. Second reagent SMS, sodium metabisulfite or sulfur dioxide. Right? So this is actually purification reaction. Purification reaction. Purification means potassium permanganate can oxidize all the organic acid, aromatic organic acid, except benzoic acid. Now here we are going to remove all other organic acid from the system except benzoic acid. Right? Reagent number 2 stop the activity of potassium permanganate. Once you finish the reaction, right? Now you can go for the next step. Next step. Right? Now we have benzoic like 4. Again, because of the sodium hydroxide alkalinity, it is again as a sodium salt. Therefore, we have to acidify it again. Acidify to convert this into benzoic acid. Acidify it again to convert this into benzoic acid. Right? Then again we have to extract it into ether. We have to extract it into ether. Then after that, we have to evaporate the ether, evaporation, and we'll end up with solid benzoic acid. COH. Right? Up to that level, if I repeat the process again, right? Generally, in food material, benzoic exists as a sodium benzoate, right? Then sample, once you obtain the sample, first we have to convert this into benzoic acid by adding dilute sulfuric acid, right? Then we are going to extract the benzoic acid into ether layer with the help of sodium chloride. Extractability increase with the help of sodium chloride, right? Then we have to add sodium hydroxide to alkaline the media. Under alkaline media, we can add potassium permanganate and sodium metabisulfite to the mixture. What will happen? Potassium permanganate oxidize all the organic acid, aromatic organic acid, right? Except benzoate. That is purification reaction. Then the next reagent activity is to stop the activity of KMnO4. That means don't add both at the same time. First, we have to add potassium permanganate for a certain period of time. We have to do the purification process. Then you can add the sodium metabisulfite to stop the activity of KMnO4. Right? Then you will end up with the sodium salt of benzoic acid because of the alkaline media. Again, we have to acidify to convert it into benzoic acid. Right? Then again extract into ether. Now ether contains pure benzoic acid. Now we can evaporate the ether layer and we can prepare the benzoic acid solid form available in the sample. Right? Benzoic acid solid form available in the sample. Right. Then we have to take this solid form. Right. Then we have to take this solid form. We have to dissolve this solid form of benzoic acid in 2 ml of acetone, 2 ml of acetone, right, and 2 ml of water. We have to dissolve this one containing 2 ml of acetone and 2 ml of water. Right. Then we have to titrate the benzoic. Right. We have to titrate the benzoic with 0.05 N sodium hydroxide. Titrate the benzoic with 0.05 N sodium hydroxide. 0.05 N sodium hydroxide. Right. Here, the benzoic is a weak acid. Sodium hydroxide is a strong base. Therefore, you can use phenol red for this type. Phenol red for this type. Acid base type. So the calculation part, 1 ml of 0.05 N sodium hydroxide equals to 0.0061 grams of benzoate. Therefore, if the reading, titration reading is VmL, amount of benzoic available in the sample V divided by W means sample weight, right, into 0.0061, that is in gram. But like sulfur dioxide, we have to convert this into ppm level, V divided by W, sample weight, into 0.0061 multiplied by 10 to the power 6. Now in ppm. Now in ppm. Now in ppm. So this is the method to use to extract the determine the benzoic acid content available in the sample. Benzoic acid content available in the sample. Right. So there are certain qualitative tests for the benzoic. Qualitative test for the benzoic. Qualitatively, you can identify the benzoic acid by using ferric chloride. Qualitatively, you can identify the benzoic, right? Using ferric chloride. That is the benzoic. COOH. If you use ferric chloride, FeCl3, right? You can obtain dark pink color. Dark pink color. Right? That is the qualitative test for the benzoic. Right. Then we will move to the another preservative. That is the sorbic acid. Sorbic acid. Sorbic acid. Another preservative. Right. First, we have to take the sample. Then you have to steam distillation. As formerly, you have to distill out this sample using steam. Then sorbic acid, like the formaldehyde, collect into sodium hydroxide. You can collect sodium hydroxide. So sorbic acid into sodium hydroxide. Then you have to mix thiobarbituric acid to it. Thiobarbituric acid. Thiobarbituric acid. That is again, thiobarbituric acid is again color complex forming a reagent. Sorbic acid form color complex with thiobarbituric acid. Sorbic acid can form color complex with thiobarbituric acid. Then you can measure the color intensity of the solution. You can measure the color intensity of the solution. Right. Before that, we have to prepare the non-concentration series of the sorbic acid. Right. Interact with thiobarbituric acid. Then you have to develop the calibration curve. Calibration curve like earlier case. Now you can very easily detect the sorbic acid content in the sample. Sorbic acid content in the sample. Right. So the next one is the color determination. Preparation of the sample and other things. Determination of food colors. Determination of food colors. It is very important in day-to-day life because nowadays people generally use non-permitted food colors for the food product, right? So once you obtain the sample, you can easily detect whether this sample contains permitted food color or not, right? So first thing is very important thing, sample preparation step. Sample preparation step. You have to be very careful in preparation of sample for the food colors determination. Because if your sample contains alcohol, you cannot directly use the sample for the determination of food color, right? So if your sample contains alcohol, you have to boil the sample little bit to remove the alcohol. Right? If your sample contains alcohol, you have to boil the sample little bit to remove the alcohol. Right? If the sample is non-alcoholic, you can directly use. Right? If it is the non-alcoholic, it does not contain alcohol, you can directly use. Right? If it is like a semi-solid, like a jam, right? Semi-solid. If the sample is semi-solid, you have to dissolve little bit of the sample in water. And make a dilute solution. Right? Sometimes your sample may contain fat like a bundi, fat and starch, bundi like sample. A confection food items. It consists of fat and starch like thing. Right? First, you have to remove the fat. How do you remove the fat? You have to interact the sample with petroleum ether or ether mixture. You can easily remove the fat from the sample. Then you have to interact the sample with 50 milliliter of 2% ammonia in 70% alcohol. Right? You have to introduce the sample to the 2% ammonia. 2% ammonia prepared using 70% alcohol. Sometimes you may think 70% alcohol is a real. That is not a real. Ammonia you can prepare using water. But in this reagent, we are going to prepare the ammonia using 70% alcohol. That's why we say 2% ammonia in 70% alcohol. Right? You have to dissolve the sample in that reagent. Right? Once you dissolve the sample in that reagent, you can observe precipitate. That means proteins and other part, carbohydrate part get precipitate with this reagent. Now with the carbohydrate and protein like parts, you cannot determine the colors. You can remove that part from the sample by using this reagent. Right? Right. Then we will see how do we identify the color. Color identification reactions. First of all, you have to select 100% cotton wool. This cotton wool, 100% cotton. You have to select 100% cotton wool. Right? And you have to put small amount of acetic. You have to use small amount of acetic and small amount of ammonia. Separate two separate dishes. Right? Now we have color extract. This is sample. Color. Right? So operation like this. First we have to dip this cotton wool in the acid. What will happen? If although this is the wool, right? This can easily absorb HAC, acid to the wool. Right? You can observe attraction of absorption of acid to the wool. Then you can dip the wool in the sample. The second one. Second step, wool in the sample. If the sample contains food color, if it is a food color, then sample easily attached with the wool. If the sample contains food color, it can easily attach to the wool. But if the sample contains non-food color textile dye, it cannot attach to the wool. If so, what you have to do? Right? If the sample does not attract the wool, what you have to do? You have to take the wool first and dip in ammonia and then in color. Right? Most of the textile dyes dissolved in ammonia. of base. Therefore, if it is a textile, then easily attracted to. Initially, we have to determine it whether it is permitted, not permitted, whether it is a food dye or textile dye. How do you check it? First, dip the wool in JC acid, then dip in the sample. If it is attached to the wool, now you can say that is a normal food dye, right? If not, you have dip the wool in ammonia and dip it again color sample. If it attached to the color, then attached to the wool, you can say that is not the food color, that is textile dye, right? Right. Now, if we think our color is the food dye. Food dye means our color absorbed to the acidic wool, acid containing wool. So how do you release the dye? Right? Now the dye attached with the wool, dye plus acid. Right? Now it can dip in the ammonia solution to release the dye. Once you dip the ammonia, ammonia absorbs the wool. In the meantime, dye comes out. Ammonia absorbs to the wool. When you dip in ammonia, ammonia absorbs to the wool. Dye comes out from the wool. Right? So this is the extraction method of the dye. Extraction method of the dye. Then you can use TLC technique, thin layer chromatography technique, to detect the dye. Which dye available in the sample? TLC technique we can use. Right? TLC technique, that means once you extract the dye, you can put the sample here. Now we are going to run the TLC under closed environment. Right? We are going to run the TLC. Right? So the mobile phase can be ammonia. 1% ammonia. Right? If you use 1% ammonia, the shape of the solvent front generally like this. Not this shape. Right? You can observe instead of this kind of shape. Right? If you use 1% ammonia as mobile phase, right? You can obtain solvent front like this shape at the end of the analysis. Right? With this kind of solvent front, you cannot easily calculate the RM value. Therefore, in addition to 1% ammonia, we can use other solvent system, isobutanol, ethanol, and water. 3 component system, 1 to 2 to 1. Other 3 components, N-butanol, water, glacial acidic acid. 12 to 5. Right? So you can use one of these solvent systems to analyze the dye. So when you run the TLC using one of these solvent systems, sometimes you will end up with this kind of picture. Right? This is the TLC plate. Sharper point, right? In the N line, right? Sometimes you can end with 2 spots at the end of the running, right? Then you can calculate the RF value, and based on your PLC knowledge, you can check the dye. Right? Once you guess the dye material, then you can run these two dyes. If it is a pure form, right? Along with this, if these two standards get the spots at the same position, now you can confirm that is the dye. But story is not like easy like that. Because in the market, instead of simple or basic dyes, they are going to use mixture of dyes. So food material contain mixture of dyes. Therefore, sometimes when you run the TLC or the dye, right? Sometimes you can end up with 3 spots, right? Then you have to rotate the TLC up to this level, right? Now you have 3 spots, right? You have to mark this and allow to run here. Again, you can separate. This is one-dimensional TLC. This is two-dimensional TLC. Sometimes you have to go for the 3D TLC because of the complexation of the dye mixture. Most of the dye mixtures are very complex, Therefore, you have to go up to the 3D analysis. Right? That is about the dyes. Then we will think about the sweetness. There are different types of sweetness available in the market. Artificial and natural sweetness. Right? Here we are going to measure the artificial sweetness or the natural one. Right? First, we have to take the sample. If the sample is solid, we have to take 20 grams solid sample. If the liquid, if solid 20 grams, the liquid, we have to take 220 milliliter. 20 milliliter of the sample plus 90 ml of water. Then it means you have to take 20 milliliter of the liquid sample and add 90 ml of water to the sample. Right? For the sample like soft drinks, we can directly take 100 ml. These are the sample taken for the sweetness. If the sample is solid, you can take directly 20 grams. If it is a liquid, you can take 20 ml plus 90 ml of water. If it is a soft drink like sample, you can directly take 100 ml of water. Right? So these are the sample quantities. Then if we think about the procedure, first we have to take the sample and acidify with dilute H2SO4. This is acidification. We have to add just few milliliter of sulfuric acid. Right? Then we are going to extract the sweetener into 100 ml of ethyl acid. First, we have to acidify. Why do we acidify? Most of the sweeteners are not in the pure form. We have to acidify. Then extract into 100 ml of ethyl acetate. Right. Then separate the ethyl acetate layer. Separate ethyl acetate layer and filter with anhydrous sodium sulfate. So what is the role of anhydrous sodium sulfate? Now we are going to remove the moisture. If there is a minute amount of moisture, we can remove that minute amount of moisture by applying this technique. Right? First, we have to extract the sweetener into ethyl acetate. Then take the ethyl acetate and filter it through anhydrous sodium sulfate to remove the moisture. Right? Then repeat the extraction. Right? Again and again, repeat the extraction to remove the anhydrous, to remove the moisture. Same sample you can use the extraction to obtain the maximum sweetener content. Right? Then you have to evaporate ethyl acetate layer. Evaporation. Evaporate ethyl acetate. That's a solvent. Right? When you evaporate, you can go up to the 2 ml residual. Right? Once you evaporate, you can decrease the volume up to 2 ml. Right? Now, your sample sweetness sample is ready for the analysis. You can use TLC. You can use TLC. Solvent system is acetone, ammonia, nitrate. You can run the TLC using this solvent system. Using this solvent system, but you cannot just observe your naked eye. Spots you cannot just observe. At the end of the running, you have to spray the TLC plate with silver nitrate. This is not a normal silver nitrate. This is not a normal silver nitrate. You have to prepare this silver nitrate in a special way. You have to prepare this silver nitrate in a special way, and then you can observe the spots under UV light. UV light, especially this is short wave. Short wave. Right. The silver nitrate solution you can prepare like this. You have to take 170 milligram of silver nitrate. To prepare the silver nitrate solution, you have to take 170 milligram silver nitrate, dissolve in water, and you have to add 5 ml of ammonia to it, and made up to the 200 ml using water. This is the preparation steps for the silver nitrate special spray reagent. Right? If I repeat it again after this level, right? First you have to take the sample, then acidify with dilute sulfuric. This is just for the acidification. Then extract into the 100 ml of ethyl acetate. Ethyl acetate is used as the extraction medium. Right? Then you have to fill the extraction. You have to filter the extracted ethyl acetate layer through sodium sulfate to remove the moisture. 2-3 times you have to follow this one, right? Then combine ethyl acetate layers, evaporate up to 2 milliliter. So finally, your sample should be 2 milliliter concentrated water. Then you have to run the DLC using this solvent system, acetone, ammonia, nitrate solvent system, right? But you cannot observe spots on the DLC plate. To observe it, we have to apply spray reagent like silver nitrate. Silver nitrate is not a normal silver nitrate. You have to prepare like this. Prepare like this means 170 milligrams of silver nitrate. You have to dissolve in water and you have to add 5 milliliters of ammonia to it and dilute up to 200 ml. Dilute up to 200 ml. Right? Then this reagent you can use as a spray reagent. Once you spray the silver nitrate on the TLC plate, then you have to observe the spots under short wave UV light. Under short wave UV light. Right? Right. If you follow these steps, the results can be like this. You follow these steps, the results can be like this. If you observe white spots on gray background, with RF equals 0.20, or white spot on gray background, RF equals 0.5. If this is a spot, this spot is relevant to the cyclamine. This is the spot, this is relevant to the saccharide. Right? So once you spray the silver nitrate, right, and when you observe the plate using short wave UV lamp, if you observe white spot, white color spot on gray background, white color spot on gray background with RF value 0.20, that is cyclamine. Right? White spots on gray background, same color, white spot, gray background, but the RF with 0.5, that is saccharide. That is saccharide. Right? That is for the example, right? But extraction method is same for the all sweeteners. Once you extract the sweetener and run the DLC and observe under the UV light, right? Then you can check the compound with the RF value, right? Right. Then we will move to the next part of this lecture series, that is the fat and oil analysis. Fat and oil analysis. Fat and oil, we are going to analyze, we are going to discuss the analytical technique regarding the certain chemical parameters. Certain chemical parameters we can use. Fat and oil analysis. First one is iodine value. Iodine value. Iodine value, if you take iodine value, so that means if the fat contain double bond, fatty acid contain double bond like this, if you interact this with iodine, this can convert into, right, iodine like this. So iodine can saturate the double bond. So this phenomenon is now used to check the iodine value. So iodine value indicate the degree of unsaturation. Iodine value of oil indicate the degree of unsaturation of that oil. Right? So to do this, we have to introduce iodine, incorporate iodine, interact iodine with the lipid. That is not the easiest way. iodine cannot just interact with the lipid. Therefore, instead of iodine, we can use another reagent. Instead of pure iodine, we can use another reagent which is highly reactive form. That is not iodine, that is iodine monochloride, ICL. When you interact the ICL with the fat, ICL with the fat like this, now it can form like this. RCH, CH, R, I and C. Right? Yes. Then this is the principal reaction. Then once you add iodine monochloride to the system interact double bond with the iodine monochloride. But sometimes we may have excess amount of iodine monochloride. Because generally we add excess amount of iodine monochloride to the system. So excess amount of iodine monochloride, excess ICL interact with potassium iodide. So in the analysis we are going to use potassium iodide and form KCl plus iodine. So once you detect the iodine we can interact with sodium thiosulfate, right? Form sodium persulfate plus sodium iodide. Plus sodium iodide. So this is the chemistry behind the analysis of iodine value. Right? That means we are going to introduce iodine monochloride to the sample, excess amount of iodine monochloride to the sample. Then certain, depending on the degree of unsaturation, certain amount of the iodine monochloride attached with the double bond like this, right? Then excess amount of ICL react with the potassium iodide, because we are going to introduce potassium iodide also. Excess amount of iodine monochloride interact with the potassium iodide to form iodine. Once you form iodine, you can evaluate iodine by the titrimetric technique using sodium thiosulfate. So this is the chemistry behind the iodine value determination reaction. Right? The most important thing is selection of the sample size. The most important thing is because without this information, you cannot analyze the iodine value. Right? That means we have to think about expected iodine value. Expected. If you know the sample, you can expect. This may be the iodine value. Depending on the expected iodine value, then sample B you can select. If it is expected iodine value less than 5, you have to use 3.00 gram. If it is between 5 to 20, expected iodine 1.00 gram. If it is 21 to 50, 0.40 gram. If 51 to 100, 0.20 gram. 101 to 150, 0.13 gram. 151 to 200, 0.1 gram. Right? So if you know the iodine value roughly of your sample, you can select sample weight based on this table. But if you don't know the iodine value, actually roughly, if you don't know the iodine value, please use very small quantity of the sample, not the very high quantity, very small quantity of the sample. Then we will see what is the methodology to detect the iodine value of the sample. We can use this method to detect the iodine value of the sample. Right? First, we have to take the sample weight, small amount of sample, and we have to dissolve the sample in 10 ml of CCl4, 10 ml of carbon tetrafluoride. Right? And we have to add 20 milliliter, that is 20.00 ml. You have to use the pipette of Vigi's solution. What is Vigi's solution? In our explanation, I explained instead of iodine, we are going to use iodine monochloride. Right? So, iodine monochloride is the unstable one. Therefore, generally we stock the iodine monochloride in glacial acetic acid. Generally, we stock the iodine monochloride in glacial acetic acid. Once we stock the iodine monochloride in glacial acetic acid, we name that solution as a Vigi's solution. Name that solution as a Vigi's. Vigi's solution contains glacial acetic acid plus iodine monochloride. We have to take 20.00 ml, that is using pipette, iodine monochloride, that is Vigi's solution. Then keep the mixture in dark. Keep the mixture in dark for 20 minutes. Then we can add 15 ml of 10% potassium iodide. Right? Here we are not going to measure the potassium iodide using pipette. Why? That is not affect to the final calculation. That is not affect to the final calculation. Therefore, but we have to use the pipette to measure the 20.00 ml, right? But not for the potassium iodide. Right? Then you have to add 100 ml of water. Once you add the potassium iodide to the mixture, what will happen? Formation of iodine, that is very dark. Right? Therefore, we have to dilute the mixture by using 100 ml of water. Then you can titrate it with sodium thiosulfate. Right? Titrate it with sodium thiosulfate. Very simple experiment. Take the sample and mix the sample with 10 ml of CCl4 because it's the fat, right? Then add 20.00 ml of Vigi's solution, which contain ICl and iodine monochloride and glacial acetic acid. Then we have to keep the mixture in dark for 20 minutes for the reaction. Then you have to add 15 ml of 10% potassium iodide to form iodine. Right? That is very dark solution. Therefore, we have to add 100 ml of water to dilute the solution. Then we can add sodium thiosulfate. We can titrate the mixture with the sodium thiosulfate with starch as an indicator. I think you know the titration. First, we have to take the sample and titrate with the sodium, known concentration of sodium thiosulfate without adding starch. Initially, don't try to add the starch to the titration. Right? But when you observe the faint straw color, very faint yellow color or straw color, now that is the point to add the starch as the indicator. Right? Then you can observe the blue color. You have to continue the titration. Blue color convert into colorless. That is the way of titration. Right? Then we will see the calculation part. We will see the calculation part. If the sample reading for the sample is a milli, the same time we have to do the blank titration without sample. Simple BMA. Which one is higher? Not like normal titrimetric method. Here, sample mean A. Titration reading milliliters. Blank mean without sample mean only which is solution. Very high amount of iodine is there. That means B is higher than A. B is higher than A. Therefore, correct reading equals B minus A, not A minus B. We can't say A minus B. If you really do the experiment, you will get very large value for the B. Right? Actually, this is not the correction. This is the most probably blank titration performed due to the correction of the reading. Here, we have performed blank titration to check whether the amount of, to get an idea about the amount of iodine monochloride available in the Vijay solution. That's why we titrate Vijay solution without sample B. Then we add this amount of Vijay solution interacted with. One is A, that is the after interaction remove, that means residual amount is A. Then by difference between B and A is amount of interacted with the sample. Right? So 1 liter of 1N sodium thiosulfate Na2H2O3 equivalents 126.9 grams of iron. Therefore, 1 milliliter equals 1 milliliter of 1N sodium thiosulfate Na2H2O3 equals 126 divided by 9 divided by 1000 grams of oil. Now our value is B minus A. That means available iodine value B minus A into 126.9 right 100 divided by 1000 now based on the iodine value definition, number of milligrams of iodine interact with the sample. Right? That's why we use this kind of calculation. W mean weight of the sample. W mean weight of the sample. Right? That is for the iodine value. Then we can put the saponification value. Second analytical reading. Saponification value. So what kind of information do you obtain through the saponification value? What kind of information? So if we take two samples, right, with three fatty acids, this one contains fatty acid A, B, C. This one contains fatty acid P, Q, R. Right. Now, weight of the molecular weight of fatty acid A can be 5, B can be 7, C can be 9. But here 0.5, 0.7, 0.9. Right? Like this. So if you really need to take 1 gram of this sample, most probably, right, this sample contains very minute quantity of the fatty acid because one fatty acid weight is a 5 because of the high molecular weight. But if you take 1 gram, here almost 2 fatty acid fulfill the 1 gram. Here 1 fatty acid. So that means when the molecular weight of the fatty acid reduce, number of fatty acid available in the 1 gram increase. Right? When the molecular weight of the fatty acid reduce, right? Number of fatty acid available in the 1 gram increase. Is that correct? That is very clear. Right? That means if we think about the initial fatty acid composition of the sample, if the weight of the fatty acid is too small, right, number of fatty acid available for the 1 gram is high. Number of fatty acid available for the 1 gram is high. When the weight of the fatty acid sample is too high, number of fatty acid available in the 1 gram is too low. Right? That is the first thing we have to keep in your mind. Right? Based on this theory, number of fatty acid available in the sample is high in this one. Not number of atoms, number of fatty acid units in the sample because of low weight. Right? Right? What is saponification? Saponification means, right, fat interact with the alkaline like sodium hydroxide to form sodium salt of fat. This is saponification. Right? If the fat contain ester linkage, definitely fat contain ester linkage. All the ester linkage of the fat break by the alkaline. Saponification means actually breakage of ester linkage with fat. Breakage of ester linkage with fat. Right? Then, if you think about the number of fatty acid available in the sample is high, mean you require more sodium hydroxide. Why? You have to break more fatty acid molecule. When number of fatty acid increase, mean molecular weight of the fatty acid available in sample is low. Right? Saponification value actually based on the number of milligrams of KOH. Actually, number of milligrams of KOH required to neutralize the fatty acid resulting from the hydrolysis of 1 gram of fat. Right? Number of milligrams of KOH or sodium hydroxide required to neutralize the 1 gram of fat. If the 1 gram of fat contains more fatty acid, it indicates that fatty acid molecular weights are very low. That's why it contains more fatty acid. If the 1 gram of sample contains lesser amount of fatty acid, that means those fatty acid molecular weights are very high, comparatively high. Therefore, we can use the phenomenon like this. Saponification value is proportional to 1 over molecular weight. So that means we can get an idea about the molecular weight using saponification value. We can get an idea about the molecular weight using saponification value. Right? Saponification value. Then we will see the methodology of the saponification value determination. So idea is to obtain the idea about the molecular weight of fatty acid, right? Right. First, we have to take the 2 gram of sample. Now, saponification or determination like this: 2 gram of sample. You have to add 25.00 ml of alcoholic KOH. Why do we use alcoholic KOH? Alcoholic KOH we are going to add. Why is the reason? Because this is a fat. This is a fat. Fat cannot dissolve in water. So if you prepare the KOH using normal water, aqueous KOH, it cannot work. Therefore, you have to use alcohol to prepare this KOH solution. Alcoholic KOH, right? Then you have to use the pipette. 25.00 ml you have to add. Right? Then you have to reflux. Reflux the mixture using water bath. Right? Then titrate with 0.5 m HCl. Phenolphthalein as indicated. Very simple technique. Right? In the meantime, you have to perform the blank titration without sample, just alcoholic KOH, and the refluxation step and the titrate directly with the 0.5 m HCl. Again, you will get two readings with sample. Reading may be simple A ml. Without sample, reading may be simple B ml. Again, what is the highest one? POA. Not like other blank. In other types of blank titration, B may be the lower. Delta titration, blank may be the lower one. Here, B mean without sample, whole thing is the KOH. Right? All KOH interact with HCl to get the highest value. Right? Again, this blank is utilized to measure the amount reacted with the sample. Amount of KOH reacted with the sample. Because now you know the amount of the KOH using this reading. Right? If the balance is A, now you can take the difference between B and A to obtain the amount of KOH interacted with the sample. Amount of KOH interacted with the sample. Right? Therefore, correct reading is B minus A milliliters. Then we can say 1 L of 1 liter of 0.5 m HCl is equivalent to 56.6 divided by 2 gram, right, of KOH. Then 1 ml equivalents 28.05 divided by 1000 in gram. of KOH. Right? Right. Therefore, saponification value equals B minus A into 28.05 divided by W is the sample weight. Now this 1000 remove with another 1000 because number of milligrams of KOH. Therefore, you have to divide this by 1000 and another 1000, 1000 cancel off. So finally, this is the value for the simplification value. Here W is the weight of the sample. W is the weight of the sample. Right. Now the next analytical value of the fat is peroxide value. Peroxide value. Peroxide value. Peroxide value says milligrams of peroxide, right? Milligrams of peroxide per kilograms of sample, right? Millimole of oxygen, actually, right? Then you have to take the 0.5 gram of sample or 5 gram of sample, 5 gram of sample. You have to dissolve the sample in a special mixture. That mixture consists of HAC chloroform, HAC CH3 C chloroform. Mixture 1 to 2. We have to prepare 30 ml. 30 ml of this mixture we use to dissolve the sample. Then we have to add 0.5 ml of saturated Ka, saturated potassium iodide. Then leave the mixture for 1 to 2 minutes. Leave the mixture. Leave it for certain time. Leave it for 1 to 2 minutes is enough. Once you observe yellow color, you can titrate it with sodium thiosulfate. Very simple technique. First, you have to take the 5 gram of sample, dissolve in 30 milliliter of solvent mixture, HAC chloroform 1 to 2 ratio, prepare mixture. Then you have to add 0.5 ml of saturated iodine, right? And if there is a peroxide, it can form iodine into solution, right? If there is a peroxide can convert iodide into iodine, this iodide into iodine, right? Once it form iodine, now iodine in a normal solution, iodine in the solution become yellow color, right? To do this conversion, we have to boil the mixture. Right? Then once you observe the iodine as a yellow color, now it indicates the sample contains peroxide molecules. Now you can titrate the evolved iodine, liberated iodine, using sodium thiosulfate as a standard solution, right? Then, if you think about the calculation part for this peroxide value And the weight of the sample is Wg, right? Titration volume is VmL, right? Normality of the sodium thiosulfate, Na2SO2O3, normality is N, capital N. Then P value, peroxide value, equals V into capital N into 1000 divided by W, that is interact. Right. That is the peroxide value equation. Again, we have to think about the again we have to think about the chemistry behind the analysis. Chemistry behind analysis is like this. When fat get oxidized, reaction with oxygen, form peroxide ROOH. When you interact this with potassium iodide, it can form alcohol ROH plus water. Right? That means ROOH convert into ROH plus water, OH plus 2 electrons. In the meantime, iodide converted into iodine is 2 electrons. Right? If you take these two equations, ROOH plus 2H plus 2 iodide convert into ROH plus iodine plus 4. This is the final reaction. Right? It's a final reaction. Then iodine interact with this iodine convert into iodine. Iodine. In the meantime, S2O3 thiosulfate convert into SO6 sulfate. Right? Plus 2 electrons. Then if we take these two equations, the final titration equation like this, I2 plus S2O3 2 iodide plus S4O6. So this is the final equation. Right? So like earlier case, you can do the blank titration. Earlier case, you can do the blank titration. Not only that, this is again ionometric titration. You have to use the starch as an indicator. First, when you titrate the iodine with sodium thiosulfate, right? Don't add starch solution at the very beginning. Why? Iodine solution. If the iodine solution is two concentrated one. Once you add starch at the very beginning, starch can form complex with the iodine. Starch can form complex with the iodine. Now you cannot break it. Therefore, at the very beginning, titrate slowly iodine with the thiosulfate. During the titration, you can observe the point. You can observe the point like faint yellow color, very faint yellow color until it comes to the very faint yellow color. Now you can add few drops of 1% starch solution, right? Then iodine can form a complex with that starch to form blue color, right? Now you know certain amount of iodine is there. Then you can continue the titration with thiosulfate to remove that blue color. That means solution become colorless, right? So that is the correct way for the iodometric titration. With that, we can conclude our lecture series, right? That is food analysis. If you have any questions, first of all, we have to think about that COVID pandemic condition. Therefore, we cannot meet time to time, right? First thing, you have to go through these videos, right? Go through these videos. If you have any questions, problematic place, right? I think you can clearly write down the place and each and every steps, right? Then we can prepare the meetings, Zoom meeting for you, right? If you really need, we can prepare the meeting, right? Then during that meeting, we can discuss further. Now you have enough stuff of the theoretical background. Now you can continue your studies with this video, right? Along with that, I think there is a practical video sessions, right? How to analyze certain compounds. Now this video session do the very big support for that, right? Theoretical support for that, right? Don't try to analyze anything without any scientific approach, without any scientific sampling technique, evaluation technique, calculation method, everything should be scientific. Everything should be scientific. Otherwise, you cannot do it. Right? So thank you very much for the viewing this kind of video under COVID pandemic. We will meet, I expect, in near future, right? Until that, I wish to very successful, healthy future for you. Thank you very much.